Welcome back everybody to a second year physical chemistry lecture, and this is the last lecture in further chemical thermodynamics. And today we are going to discuss the temperature dependence of equilibrium reactions. What will be covered and why? We have learned the origin of equilibrium constants. However, how do they change as a function of temperature? Temperature is something that we can control. It is easily controllable, easily measurable, and a very powerful variable to use to investigate chemical reactions. So it's very important to then see how an equilibrium constant, which is ubiquitous throughout of chemistry, how it behaves as a function of temperature. And this will lead us to Van Hoff's equation. What you will need: you'll need Atkinson's physical chemistry, chemical equilibrium, the equilibrium constant, previous lectures on chemical potential, and the equilibrium constant lecture. And for mathematics, we'll need calculus, both differentiation and integration. So who is Van Hoff? There's the man, Jacobus Henricus Henry van Hoff. Dutch scientist, was born in 1852 and died in 1911. He was one of the founders of physical chemistry as we know it today, and he won the first Nobel Prize for chemistry back in 1901. And he did a lot of work which included chemical affinity, chemical equilibrium, which we're studying today, chemical kinetics, and chemical thermodynamics. So the guy was quite busy. So, equilibrium reactions. What we know is that delta Rg, standard state, reaction Gibbs energy, is equal to minus RT log K when you are at equilibrium. Now, when you are at equilibrium and you have this above equation, you can rearrange it as follows. The log of K is equal to minus delta Rg on RT. Very simple, very straightforward. But how does this K then change with temperature? And if you want to see how something changes with another variable, what do? We take the derivative with respect to the variable. In this case, temperature. So, yippee! d dt of log K is equal to d dt of that delta G term. And this gives us quite a complex equation, which is the derivative with respect to log K on dt is equal to two parts, which is delta G on RT squared minus 1 on RT dg RT. Basically, we used the product rule to get what we need. However, if we are at fixed pressure conditions, we know that dg dt is essentially a derivative at constant pressure, which is, as we know, equal to minus the entropy. Thus, we can say that the derivative with respect to temperature of the standard state reaction Gibbs energy is equal to minus the entropy of the reaction. You can then get the following result. If you substitute in our entropy definition, you get out this derivative equation of log K, which is a function of temperature. The derivative thereof is equal to delta RH, that's the enthalpy of the reaction, divided by RT squared. Now, Van Hoff's equation and the Le Chatelier principle for temperature. We've just derived this equation, and what you can do is you can integrate between two fixed temperatures, and if you assume that the enthalpy is constant, you can obtain the following equation. Log K at temperature 1 is approximately that of log K temperature 2 plus this equation of delta RH on R multiplied by this temperature term. And what's very important to note is if that delta H is less than 0, you have an exothermic reaction. That means that the T2 is higher than T1, and it implies that K at temperature 2 is less than K at the temperature 1, which means a shift towards reactants. And you get the opposite case when delta H is greater than 0, and hence you have an endothermic reaction. Now that's a very interesting thing to know, that out of the above you can also deduce the entropy for free. So we just return back to our reaction Gibbs free energy at the standard state, and we can rearrange and rewrite this equation as log K equals delta H on RT minus delta S on R. If you differentiate this equation, you get the same result as before. And if you plot this equation, log K versus 1 on the temperature, and you're assuming that the enthalpy and the entropy is constant, you will get a straight line or a linear Van Hoff plot. And that is it. That's what I want to convey to you in this lecture. What do you have to remember beyond everything, of course, which is Van Hoff's equation. Log K T1 equals log K T2 plus delta H on R multiplied by that temperature term, and log K equals delta H RT minus delta SR. So one can use, in essence, the equilibrium constant as a function of temperature to deduce both enthalpy and entropy of your reaction scheme. Which brings us now to the quiz. The quiz is a multiple choice, and there are 3. They're just on 3 different slides. I'll read you the first question and we'll keep going. Question 1 is, in the linear Van Hoff plot, the gradient of the curve is, and then you've got there 6 options, and you've got to choose the right symbol. Question number 2. In the linear Van Hoff plot, the intercept of the curve is, you have to again choose which symbol is the intercept. And question 3. You determine that the enthalpy to be minus 5 kilojoules. The reaction is A, endothermic, or B, exothermic.